Hello, in this module we will learn how to do a two-sample t-test using Minitab. You will be seeing specifically Minitab version 22.4.0, but it should be similar in any recent and hopefully any near future releases of Minitab. If you're using the app version of Minitab, it should be very similar, although it's not always exactly identical. When do we use a two-sample t-test? A two-sample t-test arises when we wish to test hypotheses on the means of two samples where the variances are unknown. They may or may not be assumed equal, and the sample size is less than or equal to 30. If it's over 30, we have enough degrees of freedom to be confident that our estimate of the standard deviation is pretty accurate, and we would use a z-test. The alternative hypotheses may either be two-sided, such as mean 1 does not equal mean 2, or one-sided, such as either mean 1 is less than mean 2, or mean 2 is less than mean 1. As an example, we're going to look at an experiment conducted to determine if automotive foam seat formulation affects compressive strength of the foam. Two different formulations, mix 1 and mix 2, are of concern and are tested. 5 samples are done with each formulation. The 10 tests were done in random order, and the data is as shown in this table. We are told to assume equal but unknown population variances, but advised to check that assumption using normal probability plots. And then we're asked to use Minitab to analyze the data and draw conclusions. A good way to get a sense whether we can assume equal variances is to make a normal probability plot of the two sets of data. I've got a Minitab sheet showing here, which already has the mix 1 and mix 2 data entered in two separate columns. An alternative would be to have a column for the mix 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and then a separate column for the strengths, the first 5 being for mix 1, next 5 for mix 2. But we're going to proceed with them in separate columns here. And what we can do is go to the graph menu, pull down to probability plot, and we're going to make multiple, one for each of the two data sets. Click OK. And I already had it in there, but if I didn't, you would just pick both mix 1 and mix 2. You can highlight them both and push them over with select. So we're going to make a graph of those variables. The distribution we want is normal. And everything else, the data defaults should be just fine. So I'm going to hit OK. And this makes a normal probability plot of each of our two data sets. What a normal probability plot is a plot that uses transform axes such that if your data was drawn from a normal distribution, it plots as approximately a linear relation. In that linear relation, the left-right shift of it is indicative of the mean, and the slope is indicative of the standard deviation or the variance. And so what you see here is mix 1 in the blue versus mix 2 in the red. And if you look at the approximate line down the center of each of those two distributions, they're approximately parallel. So that would justify the assumption of using equal variances. They don't need to be perfectly parallel to get good results from the two-sample t-test. They shouldn't be grossly, non-obviously parallel. And we can already see that there appears to be a shift, although those distributions with the confidence intervals tend to overlap a little bit, so we're going to be a little more rigorous than just using this plot to answer the question about the means. But it would appear that our assumption of equal variances is justifiable, so we're going to proceed. By the way, you can double click on the plot over here and rename this. So NPP of mix 1 versus mix 2, showing we can assume equal variances. That's a bit of a long title, but you get the idea. We can rename that to something more meaningful for our particular analysis. So next we'll actually form null and alternative hypotheses. So in this case, it's mu1 equals mu2 versus mu1 not equal to mu2, where the 1 and 2 indicate for mix 1 and mix 2, mu being average compressive strength. An alternative way to write it, which happens to be what they do in Minitab, is to write h0 mu1 minus mu2 equals 0 versus h1 mu1 minus mu2 is not equal to 0. And we're starting with the two-sided alternative, even though we can tell from the normal probability plot we might have a hunch that mix 2 outperforms mix 1, assuming higher strength is better. So to do that, you go to statistics, basic statistics, two sample t. And in this case, you have your choices, each sample in its own column versus all the sample in one data. You could just use summarized data if you already have the mean and the standard deviation of it, but we have the raw data. So in this case, each sample is in its own column. And once again, I had already done this before, but you would be starting with blanks here. You can click mix 1, either hit select or just come over here and pick this. Multiple ways you can push it over there. So mix 2 select will push it over there. Now we look at the options. Standard confidence level would be 95% to look at that, to decide whether we're going to reject or not. Remember, it's mu1 minus mu2 not equal to 0, so the hypothesized difference is 0. And we're starting with not equal, two-sided alternative. Remember, we're going to assume equal variances. You might wonder, why don't we just never assume that in case we're wrong? And the answer is you get a more powerful test when it is a reasonable assumption. You're less likely to falsely accept the null hypothesis. So when it is a reasonable assumption, it's a better idea to, in fact, assume equal variances. We're going to hit OK here, and we're going to hit OK here. And we get a summary of the results here. The method is mean 1. Mu1 is the population of mix 1. Mu2 is the population of mix 2. We're going to do hypotheses tests on the difference mu1 minus mu2. And it's telling you we assumed equal variances. It gives you some summary statistics. Each sample had sample size 5. Sample means are shown there. Sample standard deviations are shown there. And then an estimate on the difference. Gives you a confidence interval estimate. We'll come back to that in just a minute. But in terms of the raw hypothesis test, it tells you the test statistic was negative 2.60, had 8 degrees of freedom, in this case n1 plus n2 minus 2. And in this case, based on the rejection criterion, the p-value is 0.031. So what does this all mean? This means that we would reject a null hypothesis, since our general rule is if it's 0.05 or smaller, we reject it. If we can be at least 95% sure in that rejection. And then in plain terms, this means that we are in fact 1 minus p, or 96.9% sure that the mix affects the average compressive strength. There is one plot that popped up here. Apparently I had that set in the plots here. Actually two plots, an individual plot and a box plot. If you come back, and by the way, Control E in a Windows machine brings you back to your last setup. So under graphs here, there's some things that you can either check or uncheck. I don't usually do the individual value plot, but I do like to look at the box plots, a nice summary. So that would just rerun the same analysis, this time only with the box plot. And from that, you're seeing, the extreme values, the median values, 25th and 75th percentile values as well. I'm going to delete this one because it's essentially redundant now. And that's a perfectly good descriptor. I'm just going to leave that as a two-sample t-test. So we might decide, since we in fact did reject the null hypothesis, we might want to reanalyze with a one-sided alternative, since it appears likely mix 1 has a lower average strength than mix 2. So if we do that, the new hypotheses are h0 mu1 equals mu2 versus h1 mu1 less than mu2. Or equivalently, and the way you'll see it in Minitab, mu1 minus mu2 equals 0 versus mu1 minus mu2 less than 0. So go back, just do another Control E to get back to the same menu we were in. The only option I need to change here is the alternative hypothesis is no longer two-sided. In this case, it's the difference is less than 0. So we do that. So in this case, we can now see the new p-value, 0.016. So we are now 98.4% sure that mean 1 minus mean 2 is negative. In other words, the average compressive strength of mix 2 exceeds that of mix 1. So if we go back to the original two-sided alternative, we could also achieve the same understanding of the result of rejecting null hypothesis by looking at the confidence interval difference here. So we're 95% sure that the difference between mean 1 minus mean 2 is somewhere between negative 306 and negative 18.5. Since that is unisigned, meaning always negative, does not include 0, we're sure that that difference is negative. So we could have interpreted the confidence interval basically the same way, saying we're at least 95% sure that the two mixes affect the average compressive strength. If we go back to the one-sided confidence interval, you'll see the same thing here, where the 95% upper bound is still negative. So 1 minus 2, the upper bound on that at 95% confidence is still negative 46.4, and that's because we're actually a good bit more than 95% sure. We're 98.4% sure. I'm going to right-click on this and ask for a few more decimal places. Based on that 0157, we're actually 98.43% sure that mu1 minus mu2 is negative. So just to show what happens to the upper bound there, it should approach very close to 0 at that level of accuracy. So if we come back here, change the options, now instead of 95% confidence level, if we go 98.43, that upper bound should approximately be 0. It's not going to be precisely 0, more than likely. And it becomes 0.1, very close to 0. So we're basically 98.43% sure that the difference is negative, meaning mu1 minus mu2 is negative, or mu2 exceeds mu1. Same conclusion by interpreting the confidence intervals that we would get with the t-test directly. If you go back to the original confidence interval, you have to be a little careful because there's actually 2.5% above 18.5, 2.5% below negative 306, the alpha by 2 effect. So that ends this example. If you want to see the theoretical calculations, if you're so inclined, done in Excel, that will be made available as a separate video. Thank you.